Guys, I'm Gurveer and I'm covering the topic to calculate energy of photons in electron volt, maximum kinetic energy, work function and threshold frequency from the chapter dual nature of radiation and matter. So we'll do this topic with the help of a numerical. So this is the numerical right here. This is photoelectrons are emitted from a metal surface when a UV light of wavelength 300 nanometer is incident on it. The minimum negative potential required to stop the emission of electrons is 0.54 volt. So in this numerical we are given two things. So let's note it down first. So the first thing is wavelength, that is lambda is equals to 300 nanometer. As we know that 1 nanometer is 10 raised to power minus 9 meters. So lambda is equals to 3 into 10 raised to power minus 7 meter. And the minimum potential required, which is also known as stopping potential V0, is 0.54 volt. So what we have to calculate in this numerical is first the energy of the incident photons in electron volt, second the maximum kinetic energy of the photoelectrons emitted, third the work function, fourth the threshold frequency, which is V0. So let's begin with finding the energy of incident photons. Now we know that energy is Planck's constant into frequency, that is h nu, and we know frequency is equals to c upon lambda. So from this we know that energy is hc upon lambda. Lambda is wavelength and c is speed of light in vacuum. So here h is 6.63 into 10 raised to minus 34, which is Planck's constant. C is speed of light in vacuum, which is 3 into 10 raised to power 8 meter per second. Lambda is wavelength, that is 3 into 10 raised to power minus 7 meter. And so energy is 6.63 into 10 raised to power minus 34 multiplied by 3 into 10 raised to power 8 divided by 3 into 10 raised to power minus 7, which gives us 6.63 into 10 raised to power minus 19 joule. But it is in joule, we have to find it in electron volt. So we know that 1 electron volt is 1.6 into 10 raised to power minus 19. So energy now becomes 6.63 into 10 raised to power minus 19 divided by 1.6 into 10 raised to power minus 19, which gives us 4.14 electron volt. So this was the energy of emitted electrons. Now the second thing that we have to find is the maximum kinetic energy of the photoelectrons. Now we know that Kmax, that is maximum kinetic energy, is E into V0, that is electron into V0, that is stopping potential, and we know stopping potential is 0.54 volt and E is 1. So Kmax, maximum kinetic energy, comes out to be 0.54 electron volt. Now the third thing that we have to find is the work function, that is W0. Now we know that Kmax, that is maximum kinetic energy, is h nu minus work function, that is W0, and now taking work function W0 on the other side, we get W0 is equals to h nu minus Kmax. On putting the values, we get work function as 3.6 electron volt. Now the fourth thing that we have to find is threshold frequency, that is V0. Now the threshold frequency, we know that work function, that is W0, is equals to h nu naught, that is Planck's constant, into threshold frequency. So now we have to find the threshold frequency, that comes out to be work function upon Planck's constant, and work function here is 3.6 electron volt, and the Planck's constant is 6.6 into 10 raised to power minus 34. And so threshold frequency now comes out to be 3.6 upon 6.6 into 10 raised to power minus 34 hertz. On solving, it gives us 5.45 into 10 raised to power 32 hertz. So I hope that you are clear with the topic and you have understood the numerical. Thank you for watching the video.